Okay, so this is the first official podcast in the Mind in Context podcast, and it's going to delve into issues in the field of the key issue in the field of kinesiology, and particularly the arm of motor control. So the field of kinesiology has three main arms, as far as I'm concerned. There's motor control, which is just how does the mind-brain sort of complex control the operator, which is the body, right? The musculoskeletal system. How does the mind and nervous system interface onto the musculoskeletal system to cause human and animal motion? And and that's one branch of kinesiology. The other branch of kinesiology is motor learning. So how is practice structured in such a way that you can in fact develop skillful motor movements? And I'll get to that later. And the other arm is exercise physiology. So that takes into account the cardiovascular and system, which says that okay, human beings need nutrients and energy to move. How is that used up, and what's the sort of the transfer process from sort of consumption to movement? And that's where even nutrition really the interface of exercise physiology, sort of where nutrition and kinesiology sort of meet. Anyways, so human motion, regardless of the joint segment, or even if you study the center of mass, so that's just the aggregate of all the different limbs. There's something called repetition without repetition in the system, and the big question is whether that repetition without repetition is a feature or a bug. By feature, I mean, is it a good thing or is it a bad thing? And then there are many issues with how we estimate this repetition or lack thereof, and that's sort of the first big question. I'm not going to dive too much into that yet, because there are many measures, and some come from linear statistics and non-linear statistics. And we'll dive into that maybe if I get the chance to. And just to clarify the first question a little further is how do we reduce continuous human motion into an ensemble variable so as to compare groups and even individuals over time in the context of motor learning? As a result, is it important? It is very, very important to reduce continuous human motion into ensemble variables, and this is most pertinent in fields like, so a lot of people study locomotion. So locomotion is human walking, human running, even human skipping, right? And so the big question there, and wheelchair motion, right, and even using a walker, right? This is all just forms of locomotion, of human movement, and they're continuous, which means that they have a duty cycle, which means they repeat sort of the same thing over and over again. So walking, you have heel strike to initiate it and a toe off at the end, and then the next heel strike. And that's a duty cycle that's repeated often and often over again. And so a big question that we ask ourselves in the field of kinesiology is that do we estimate sort of the ensemble variable? So you need to somehow, you can't study every duty cycle by itself, otherwise you're looking at the whole picture, and you're trying to reduce it into a function, right? You're trying to reduce it into a simple function, and that's the issue here. Is that, so do we estimate the simple function of somebody's walking using linear statistics, but that just the mean and the standard deviation or the covariation, or do we use estimates from nonlinear statistics such as the detriment fluctuation analysis or power law scaling? And all these they're just simple functions that represent that represent continuous motion. So what you notice is that a duty cycle is something like a sine wave, right? And a sine wave can be reduced to a simple function. Right? You don't need to look at the whole thing. If you know what the function is, you can just sort of estimate. You can then calculate for what it looks like. So, but we need to reduce continuous motion into continuous signal. There we go. Continuous signal into a simple function, and that's what we can do with linear statistics and nonlinear statistics. So the argument for using, so I've sort of accepted that we need to use nonlinear statistics because the human motion system, so from the mind, the nervous system, the musculoskeletal system, is highly nonlinear. It's highly fractal, and they're interconnecting parts, and the system itself is not linear, and as such, it makes sense to use nonlinear values. Okay, that's fair. I accept that. However, these variables are hard to interpret, right? Because they were developed in fields of really highly technically and highly confusing matters. Like they were developed from the field of complexity science and chaos theory and things like that, and statistical mechanics. And these are highly complicated fields that are far removed from the human system, and as such, it makes it rather difficult to move the ideas from there to our human system. And that's something I was trying to bridge in my PhD program. Didn't quite get as far, but I have time now, so I'm going to really explore it. So if we accept the nonlinear statistics that they're the best way to get to a composite function of human continuous motion, the question is then what does it mean then, right? If it's higher in one group, or if the function looks a little different in one group versus another group, does it have any implications? And if it changes over time in a person, does it have any implications? I really was rather interested, and I still am really interested in sort of the implications of changes in the fundamental function, right, as developed through nonlinear statistics. So to phrase it with respect back to the initial question, when does a change in this nonlinear function, a statistic, mean more repetition, and when does it mean less repetition for one? Are there any negative consequences for either more repetition or less repetition? So there's an argument that too much repetition is bad and too little repetition is also bad. So you get this sort of U-shaped function where sort of human coordination ability, let's call it that, is too bad when it's too rigid, as in it's too simple, which means you can plot it with just a sine wave, or when it's too chaotic, where there's no semblance of repetition in there. However, the evidence isn't strong enough in my opinion, because it hasn't shown any direct consequences. So in a related field, in the field of cardiology, it's been shown, like using a prospective study of people dying in the future. It was done primarily with a group led by a man named Louis Lipsitz. And aging also, the field of aging has shown that when humans during the aging process, there's a certain loss of complexity that happens, and that loss of complexity has been shown to lead to a lot of dire consequences, and that's fairly solid. Aging and cardiology have a solid showing that loss of complexity, that is too much repetition without enough variability, or too much chaos, too much variability without enough repetition, and prospectively predicts death due to heart failure or other aging side effects. And that's solid ground to stand on. However, it's very compelling evidence. However, the field of kinesiology, motor control, doesn't have an experiment that's just as strong, right? And as such, we need to do that key experiment, right? And the closest we've come to that is that falls, sort of accidental falls, because again, nobody falls down, because again, the falls can have rather dire consequences. Nobody has really done this sort of prospective experiment in the area of kinesiology by sort of inducing falls and seeing if there's any relationship between motor sort of human locomotion, coordination, and falls. The closest we have is with respect to retrospective studies, in which we're seeing that, okay, maybe loss of complexity and maybe too much rigidity is in fact related to retrospective falls. And what the issue with that is that when you're looking at historical data, right, like that, there could be a lot of spurious correlations, right? It could be that it's not in fact the coordination that is leading to the falls. Maybe it's some other factor that this group shares together, right? And as such, we need to do the prospective experiment, right? And there are many ways to do this. There are two key ways you could do it, and I've come to one that I think is more rigorous. But there are two key ways you could do it. It can be done in the laboratory by inducing a scenario that may result in a fall, while factors that may either increase or decrease variability are either augmented or reduced. By that, I simply mean that there's a group in North Carolina that has a system whereby they can induce, sort of by changing the visual field, they can induce more variability or less variability. And as such, we can then, in that context, we can then induce a scenario that could lead to fall. We can either trip them or slip them, and see if there's a fall or no fall that happens afterwards. That's one approach. And the other way you can do it is by estimating sort of this variability function in a laboratory during walking, and then sending people out into the world and measuring fall or no fall incidents. So they both have their pros and cons. The first one, the one of doing the laboratory fall, it's easier to control, and the correlation between sort of changes in variability and sort of fall incident will be less spurious, right? However, laboratory settings change motor coordination, right? So they could fall for other reasons, but it's less likely so, right? But the biggest issue though is that in the real world setting, the big negative there is that the correlation between walking variability as estimated in the laboratory and fall or fall no incidents will be more spurious, right? By that I mean that it's harder to connect what happens in the lab and what happens in the community, right? Because people fall or don't fall for very, very many reasons, right? And as such, from a rigorous point of view, the laboratory scenario is the best way at getting at whether or not correlation between walking variability and fall or no fall in fact is related. And so that's something I was going to try and pursue in my PhD, and something I'm still going to try and look into. But anyways, that's the first episode.